little recap from last time. So we have the atomic models. We have the Bohr model that exists in certain energy levels, corresponding to how much energy they have. There can only be specific energies. They gain energy, move to higher ones, they lose energy, and move to the other ones. So you could think in the Bohr's model, the electrons are in orbit at a certain energy level around the nucleus. Can one of y'all close the door? We then have the quantum mechanical model, or the electron wave model, or the electron cloud model. In which case, the electron is a cloud of probability. We have a density of it, and this fuzzy cloud represents 90% probability of finding it within it. Electrons don't have definite positions. We have an atomic orbital, which is what we're going to get into. So this unit is all about atomic orbitals. So this is the most simplest. The s orbital. They're spherically shaped. Smaller atom has fewer electrons that take up less space. Larger atom, more electrons take up more space. So an s orbital is just a sphere. Electron just randomly in some place in the sphere. We have a p orbital, a dumbbell shaped. There are 3 of them. You can think of it in 3D space. There's an x-axis, a y-axis, and a z-axis. So here's in the z-axis, the x-axis, and the y-axis. So 3 p orbitals. All together, you get your 3 p orbitals, x, y, and z. It makes up this shape. We then have d orbitals. It's kind of like 2p orbitals squished together. And then we have f orbitals. There are 7 f orbitals. And they make up all these shapes. Some of them are just rotated versions of them, but we can look at the f orbitals and see that we get very complicated shapes. The d orbitals, 4 of them are just rotations of each other, but if you look at the very right one, it's weirdly shaped. So these 4 right here are just rotations of each other, but this 5th one is very uniquely shaped. These p orbitals are just rotations of each other. F orbitals are very weird. We got 2 rotations right here. And the rest of them I think are unique. So shells and orbits, or orbitals, and atomic structure. Shells of an atom contain a number of stacked orbitals. See if I can find the better representation of the difference between a shell versus an orbital. So the orbitals are the individual orbits or orbitals. So the P shell would be all or should I be subcells? So we have orbitals. They're the individual ones. So the z-axis of 2p and the z-axis, 2p and the x-axis, 2p and the y-axis. Each of these individually are called orbitals. Now all p shells on the same energy level would group together to be called a subshell. Now the entire energy level is known as the shell. So shell is just another word for energy level. It's more encapsulating though. And all the p orbitals make up a subshell. There's only going to be one s orbital, so but it would also be a subshell. And then everything on the second energy level is known as the shell. So all these stack together. So if we were to look at, for example, this one, we see 1s, we see a 2s, and then we see 3 2p orbitals. They all stack together, and this is the reason why atoms look spherical, because all these orbitals all stack on top of each other and overlap. And so we end up, they all twist around each other and trying to get as distributed as possible, and this gives it an overall spherical shape. Different atom orbitals are donated by letters. The s orbitals are spherical, the p orbitals are dumbbell shaped. So there's an s orbital, there's a px orbital, a py orbital, a pz orbital. Usually we don't include the x, y, and z. There's a dxy, dxz. You don't have to know the subscripts, as I don't have you name each one. So the numbers and kinds of atom orbitals depend on the energy sublevel. Not to be confused with subshell. This is a sublevel. The number of electrons allowed in each of these first 4 energy levels are shown below. So this is important to know. A maximum of 2 electrons can exist in any orbital. So if I go back, in each of these orbitals, at most, only 2 electrons can exist. In the first energy level, a maximum of only 2 electrons can exist. In the second energy level, only a maximum of 8 can exist. In the third energy level, 18 can exist. In the fourth energy level, 32 can exist. There's a nice formula. It's 2n squared. So 2 times 1 squared is just 2. 2 squared is 4. 4 times 2 is 8. 3 squared is 8. 3 squared is 9. 9 times 2 is 18. 4 squared is 16. 16 times 2 is 32. So you can figure out how what the maximum number of electrons in that energy level can be. And again, there's only 2 electrons per orbital. Everyone good? So the number and kinds of atomic orbitals depend on the energy sublevel. So a sublevel is going to be the S, P, D, and F. I guess technically you could think of it as a subshell. So in the first energy level, there's only one type of sublevel or subshell. I guess you can still call it subshell, and it's the S. Only the S orbital can exist in the first energy level. The maximum number of electrons in a S orbital is 2. In the second energy level, S and P can exist. There are 3 p orbitals and 1 s orbital. So for each of the 3 p orbitals, 2 can go in each. So that gives you 6 total in the p orbitals, p subshell. And 2 can go in the s orbital, giving you 6 plus 2 for 8 in total. In the third energy level, S, P, and D can exist. You'll need to memorize the fact that 1 s orbital, 3 p orbital, and 5 d orbitals. So 2 electrons per d orbital gives you 10 in total across all d orbitals. 2 for each of the 3 p orbitals gives you 6. And 2 for the 1 s orbital gives you 2. Add them together, we get 18 total electrons in the third energy level. The fourth energy level can have S, P, D, and F. And again, same thing, there are 7 f orbitals. So that means 14 electrons can go in all the f orbitals, 10 can go in the d orbitals, 6 can go in the p orbitals, and 2 can go in the s orbitals, giving you 32 in total. There is only currently known about S, P, D, and F orbitals for the periodic table of elements we discovered so far. So the ways in which electrons are arranged, don't need me to go back. The ways in which electrons are arranged in various orbitals around the nuclei of atoms are called electron configurations. 3 rules: the AFU principle, the Pauli exclusion principle, and Hund's rule tells you how to find the electron configuration. And this is mainly going to be what the test is over, I believe, is electron configuration. You need it's important to know where all the electrons are in the atom and to determine the valence electrons. There are exceptions to rules, but in this class, we're not going to go over the exceptions. We're going to assume that everything perfectly behaves to these 3 rules. I will discuss the primary exception that you'll encounter, but I'm not going to count wrong if you ignore the exception and put the configuration that corresponds to this rule. So, off-ball principle. According to the off-ball principle, electrons occupy the orbitals of lowest energy first. In the off-ball diagram below, and I'll show it to you on the next one, each box represents an atomic orbital. So electrons want to fill the ones that have the lowest energy first. Now, you may think that each energy level is increasing energy. That the third energy level is more energy than the second energy level. That is not the case. We'll see in a little bit that it is somewhat the case, but we'll see here in a little bit that we won't fill the entire, for example, fourth energy level before we move on to the fifth and sixth. Kind of jumps around, but there's a very nice diagram or technique for figuring it out. The second one is the Pauli exclusion principle. According to the Pauli exclusion principle, an atomic orbital may be described by at most 2 electrons. To occupy the same orbital, 2 electrons must have opposite spins. That is, the electron spins must be paired. Hund's rule states that the electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin as large as possible. So, what the Pauli exclusion principle states is we can have at most in one orbital a spin-up electron and a spin-down electron. Hund's rule states that in a subshell, such as the 3p's, if we were to add, so let's say we have 3p's orbitals, that means at most 6 electrons can go into all 3. If we were to add in an electron at a time, by default we usually assume spin up, but it could be spin down, it doesn't really matter. But let's say we added a spin up electron. So the spin is pointing upward for the electron, it would go into one of the p orbitals. Let's say px. The next electron will match the previous electron spin, because according to Hund's rule, electrons tend to increase or make the spin direction as large as possible. So we'll end up with 2 spin ups, and because of the Pauli exclusion, they can't go in the same orbital. So px will have 1 spin up, py would have another spin up. So, animate it a little bit. So imagine this box being an orbital. Let's say this one's px, this is py, and this is pz. So this is a subshell, and each of these are orbitals. So let's say that, so Pauli exclusion says that we can have at most a spin up and a spin down in a box. Pauli exclusion. At most, 1 spin up, which is usually written with a upward facing arrow, and 1 spin down. Spin is a quantum mechanical property of subatomic particles. At one point, they thought it was actually rotating, but they found that it's a single point, and a single point can't rotate. So it's just a quantum mechanical property that we just misnamed and called it spin. Just like we name these orbits. They're not orbits, they're orbitals, but the orbit part of it keeps in the name. It's just later we found out that's a horrible name to call it because of quantum mechanics. But we have a spin up and a spin down, and an electron is either spin up or spin down. If you could imagine it being spin at a different angle, quantum mechanics would say that it would be a combination of both up and down. Very complicated stuff, but Pauli exclusion just says that we have at most 1 up and 1 down. Hund's rule states that we try to maximize the same spin. So I'm going to show you how you would add 6 electrons. So if I were to add 1 electron, I'm just going to arbitrarily choose spin up. By default, I always start with up. It could have been a down, it could have been it could be an up or a down, it doesn't matter, but usually by default we just start with up. So that's 1 electron in the subshell. To add a second one, 100 tells us maximize same spin. So we have 1 spin up. To maximize same spin, we're going to need to add another up. But 100 tells us that we cannot put the up in this orbital, because at most only 1 spin up can be in there. So we'd add a spin up right here. So the py orbital will be filled. If we add another electron, we're going to want to maximize the amount of up orbitals, so it start and fill the pz orbital. So having 3 electrons in a subset of the p subshell means that we'll have 1 electron in each orbital. If I were to add a 4th electron, well, no more up electrons can go into the shell. The ABBA rule says that we're going to continue filling this energy level. And so I'll have to add a down orbital here. Or down electron, down spin electron there. If I add a 5th one, it would have to be going somewhere. Usually for neatness we go left or right. It really doesn't matter which orbital it goes into, but usually for cleanness we by default start with up and we do it left or right. So this would be 6 electrons completely filling the subshell. We have an up and a down per orbital and a most of 6 electrons per p orbitals. Now, off-ball principle. This is how I recommend. Start with numbering 1 through 7. And these will all be your S's. You start with S. Next, we're going to skip 1. And we're going to renumber, starting with 2. So each row is going to share the same number. Each column will share the same letter. And these will be your P. So P follows S's. And again, we're going to skip the number, and we're going to start with 3 and go up. And these will be your D's. And next we're going to start with 4 and go upward. And this will be your F's. You can leave it like this, just fine. But if you look up at this image here, you notice the 7s are incomplete, the 6 is missing 1. It does not matter to the calculation if you just write it like this. So technically these two 7, 7D and 7F doesn't exist. Or I should say there is no atom that has, in the ground state at least, an electron in 7F. And none in 6F. But it doesn't matter when doing the calculations. You're just not going to wind up with anything in 7F. So off-ball says, or off-bow, or however you pronounce it. We begin with the lowest, fill the lowest first. So off-ball principle, fill lowest energy subshell first. So what is the lowest energy one? That would be S1, or 1S. So 1S is the lowest. The second lowest is 2S. The third lowest is 2P. And then 3S. The fifth lowest is not 3D, but 3P. And then 4S. The next lowest is 3D, then 4P, then 5S. You notice I'm drawing them in the diagonals. So note that all the 3's are not grouped together. 4S has a lower energy state than 3D. So if you can make this diagram and just draw the diagonals, you have the correct order of the energy levels. If you want to continue it, we have 4D, then 5P, then 6S. Then we'd have 4F, 5D, 6P, 7S, and then 5F, 6D, 7P, and technically these last three don't exist. So when you begin writing in the electrons, you're going to begin with 1s. How many electrons can go into an S or subshell? So remember, the S subshell, there's only one S, so at most 2 can go in. So 1s2. Again, for 2s, at most 2 electrons can exist in the s orbital. For p, this represents the entire, so this right here represents 2px, 2py, and 2pz. So there are 3p orbitals. Each one can have 2. And so we get a total of 6 electrons. And then 3s, there can only be 2 in s. And then we get p. P can have, so if you just remember that s is 1 orbital, or 2 electrons, so orbital. So we have subshell s, number of orbitals, 1, and electrons is going to be twice. E, there's 3, so 6. D, there's 5. They're just the odd number, so there's 10. And F, there's 7. So you just double it, 14. So you memorize this. For the P, there is at most 6, and 4s is at most 2, and then when we get 3d, 3d can have up to 10 electrons in it. And this would be an electron configuration. And to figure out what electron configuration this is, we have 2 plus 2 plus 6, that's 10, 2 plus 2 plus 2, 10, and then another 10. So there are 30 electrons. And looking at my periodic table, that would be the electron configuration for zinc. So this would be zinc's electron configuration. So a zinc atom is 2 electrons in the s or 1s, 2 electrons in 2s, 6 electrons in 2p, and this would be how it's ordered. I prefer that you keep it in this order. However, on some tests, they alphabetically sort them. So that is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2. So this is off-ball sorting. I do it in accordance to off-ball energy level. Some places will put all the 3s together. I don't like that. I like keeping it how it is, how you actually solve it, keeping it in the same order. So the electron configuration of an atom is the shorthand method of writing the location of electrons by sublevel. So the energy level is going to be 2. The energy sub-level or subshell would be P, and the number of electrons is a superscript. It's a number on the energy sublevel. So the sublevel is written followed by a superscript with a number of electrons in the sublevel. So if the 2p sublevel only contains 2 electrons, it is written as 2p2. By the way, this is shorthand. So there is longhand and shorthand. So 2p2 is the shorthand. The longhand version is we have 2px, 2py, and 2pz. This 2 tells us that there are 2 electrons. And according to Pauli exclusion and Hund's rule, we would maximize the amount of same spin, and so we would have them go into these orbitals like this. So the shorthand only uses subshells, while the longhand version actually writes out the individual orbitals. If the 2p sublevel contains the electron, it's written as 2p2. So let's write some electron configurations. So what is the electron configuration for iron? What's the first thing we need to know before writing the electron configuration? What do you think the first thing we should do? Figure out how many electrons we have. How many electrons do we have for iron? And we'll assume it's a neutral atom. So we have 26 electrons. Alright. What would be the next step? Filling out the sublevels according to Aufbau's rule. So what comes first? 1s, then what? 2s, then 3s. So remember, our s's, and we'll go have our p's, and then we'll have our d's. So we're going to do 1s first, then 2s, then 2p, 3s, then 3p and 4s. Oh. So 1s first, then 2s, then 2p, 3s, then 3p, 4s, and then the next one, would be 3d, 4p, and then 5s, giving up that way. And I'm going to stop there and see if we have enough. We might have done too many, but it doesn't matter. We'll just remove what we have. So iron has 26 electrons. We know that in S, there's only one orbital and at most 2 electrons. A P, there are 3. A D, there's 5, so the odd numbers. And at F, there are 7. The number of electrons will be twice, so 2 times 3 is 6, 2 times 5 is 10, 2 times 7 is 14. So we have 26. This is the amount of electrons we have, and we're going to fill this up until we run out. So I'm going to add 2 here. That gives us 24 left. 2 here, 22 left. 6 can go in here. So that would be 16. 2 can go into the s orbital, 14. P can have 6 more. So put 6 in there. That'll be 8. Got 8 left. 2 can go in the 4s. And a 6 left. And D can hold 10. But we only have 6 left. So I'll put 6 there. And this is the electron configuration for iron. So the the 3D subshell is not completely filled. Only 6 of the electrons are in it. So first determine how many electrons are in an atom using the periodic table. Iron is 26. Then we arrange the energy sublevels according to increasing energy. This is just Aufbau's principle. Then we fill each sublevel with electrons until you have used all the electrons in the atom. To make it easier for you guys, this is what I do so I was doing 2 for that one, 2 for that one. It is very easy to miscount and get this off. So if we look at 1s2, 2s2, and 2p6. 2 plus 2 plus 6 is what? 10. So 2 plus 2 is 4. 4 plus 6 is 10. And if we look at the next, so the first 3 are going to be 10. And if we look at the next 3, that's 3s2 and 3p6 and 4s2. So 2 plus 6 plus 6 is also 10. So that makes it somewhat easier if you can almost always group by 3 for the first 6 and get an even 20 off of it right there. I highly recommend that once you're done, go back and add all the numbers together and make sure you have 26. I group by 10. This is 10. That's 10. And we have 6. 10 plus 10 plus 6 is 26 electrons. The last step is the sum of the superscripts equals the atomic number of iron. Note that these electron configurations, when I ask you to write an electron configuration, I'm asking for the ground state. Ground state is when the electrons are all at the lowest possible energy level, and also a neutral atom. So, what would be the ground state electron configuration for a neutral atom potassium? If I just ask for an electron configuration, assume neutral atom and assume ground state, we can have electrons jump up into higher orbitals, but for the most part, we'll assume that that's a ground state and it's a neutral atom. So what would be the electron configuration for potassium? And how I just filled this out is how I always fill it out. So I go up to 7, but we're not doing anything with 7 right now. I'm not doing anything with F either. So potassium has 19 electrons. So we're going to go in this direction. 1s, 2s, then 2p, 3s, then 3p, 4s, and 3d, 4, so 3d, 4p, and 5s. I know that the first 6 is 20, so all I need is the first 6. 1, 2, 3, 4, 5, 6. So these I don't need. I know the first 3 can hold 10. So 2, 2, and 6. This can hold 10, but I only have 19. So 19 minus 10, I have 9 left. 2 and 6, 8. So minus 8 gives me 1 remainder, and that 1 remainder will go here. So this is the electron configuration for potassium. The 4s sublevel is only half filled. Because we're running out of time, I want to show an ion. So this is not a neutral atom. It has a charge of 2 negative. What does 2 negative mean? So if it has additional 2 negative charges, that means what? Yes. So normally, O has 8 electrons. O2 negative has 10 electrons. So we do the same thing. 1s2, 2s2, and 2p6. 1, 2, 3, 4, and 4 plus 6 is 10. So, and last step, oh no, that's it. So this is the electron configuration for O2 negative. Which, if we look at neon, neon by itself has 10 electrons. And this is also the same configuration as neon.